So, we are back again. We are going to discuss about the limits and continuity of two variables. Limits is okay, we are not going to stress too much on finding limits, because this whole issue of finding limits will come when we are going to talk about continuity. So, what do we mean by continuity? Again, if I go back and try to mimic the definition that I have learned for real variables, continuity would mean the following. But what does it really mean in terms of the neighborhoods that we have defined in the last lecture? This is crucial. So, if I am talking about continuity, my thing would be as follows, that given any epsilon, there would exist a delta greater than 0 such that the difference between f x, I am meaning continuity at xi eta. So, basically continuity at xi eta. So, f x y minus f xi eta is less than epsilon whenever the distance of the point x y from xi eta is strictly less than delta, that is root over x minus xi whole square plus y minus eta whole square is strictly less than delta. That is the meaning of continuity. Of course, you can say, okay, can there be anything in terms of sequences which we have learned in functions of one real variable? The answer is that suppose you have a sequence xn converging to x and a converging to xi and a sequence yn converging to eta, then limit f of x and yn as n tends to infinity. So, basically now I am looking at the sequential limit of the function. This is same as f of limit xn limit yn, and that is same as f of psi eta. Let us go through it again. It is always important to go through things which are not so easy to understand. So, I am trying to now mimic the definition of what I have learned in functions of one real variable. In that mimicking, give me any epsilon, I can show that the distance between the function values is strictly less than epsilon whenever the distance between the 2 points is strictly less than delta. But this distance is not just taking the absolute value, because you know the distance that we have defined in case of functions of two variables is pretty different. This is exactly the distance. Basically the delta, the R neighborhood we are talking about, sorry, this should have also been R neighborhood, I corrected. So, the R neighborhood that we are talking about, this is exactly the distance. So, whenever the distance is within a given R, so which means that if I want to write it more precisely, I can write that mod f of x y minus f of xi eta is strictly less than epsilon when x and y is in the ball of radius delta and centered at xi eta. This ball of course means the open ball, you just from the definition of the previous day. This is exactly the whole thing. So, once we have done this, it is important to know how to detect continuity of a function of two variables. Let us know some, let me tell you one thing, function of two variables, things are very strange. a function of two variables can be such that if you fix up the y, make it a constant, then it is continuous in x. If you fix up the x, that it becomes just a function of y, it is continuous in y, but it may not be continuous at every point on the as a function of x y. Finally, we have to understand when you are looking at functions of real variables, when you are talking at points of discontinuity, they are only one point of discontinuity. Here the function can be discontinuous along a whole curve and things can be quite different, and that is the sort of thing that I want to show you right here before we go into any further discussions. Okay. Let us for example talk about the function say z equal to y by x, and that is your f of x y. So, this is an example. Now, this is defined for x not equal to 0, and we say that z is equal to 0 when x is equal to 0. Or if you don't want to write it in this cryptic fashion, you can write it at f x y as y by x when x is not equal to 0 and is equal to 0 when x is equal to 0. Do we have continuity? Now, suppose I fix up the x, say I put x equal to 2. So, if I look at this function f 2 y, what does it mean? Now, it becomes a function of one real variable. This is nothing but y by 2. Now, as a function of y it is continuous, of course, it is continuous, it is obvious, it is just a linear function. So, you see this happens. Now, if I fix my y and vary my x, what would happen? Then this function is say 2 by x when x is not equal to 0 and equal to 0 when x is equal to 0. This function becomes discontinuous as a function of x. Now, let us look at this function f x y equal to y equal to x. This is discontinuous only at 0, at the point 0 say, when I am fixing up y and allowing x to move. Now, if I look at this function f x y, take all the points x y, all or take the line where you have x equal to 0, means basically the x axis is the y axis. So, I am this line on y you have x equal to 0. So, y this line is same as x, the line x equal to 0. So, if you are taking x equal to 0, what I want to tell you is that along this line x equal to 0, this function is discontinuous. It does not have a your left continuity and right continuity will become different. So, can you try to prove this fact? So, take any point here on the boundary which is 0 and say eta, then what you can do? You can move from this side, say suppose, or you can move from this side whichever way you want, and you see if you move from this side you have negative values of y. Now, suppose we are approaching by these two parts. So, in this part, of course, now at this point if you take an x is not 0, right. So, you take this point, say these are the points. So, at this point x is not 0, at this point x is not 0. So, it is y by x. At this point y is negative and here x is negative. So, it will give me the positive thing, it will give me the positive thing, right. Now, so the limit would be same, but now suppose I approach from this direction to 0 eta and you are approaching from this direction. So, if I approach on this direction I have x 0. So, my limit is actually 0 0 0 0, the f values are only 0 on this line, but when I am approaching 0 eta from this direction the limit would be finally positive. it would actually blow up, because you are bringing x towards 0 and you are bringing y towards eta. So, this limit would actually blow up. So, then the left limit and the two limits from two different paths do not. So, if you come by this particular path, then limit y by x as yx tends to as xy tends to 0 and eta, this will blow up, this will just shoot up. While if you are coming on this line here, because x is always 0, the function value is 0. So, limit of y is approaching eta, because x is always 0. This function value f of x y is actually 0, because x is 0. So, limit y approaching eta 0 is 0. So, when you approach through 1, the function value blows up. Through approach to other approach, take the approach to the y axis, the function value gives you 0, the limiting value is 0. So, you see the limit does not really exist at 0 eta. So, the limit is not really existing at 0 eta. So, it is true for any point on this line. So, you cannot talk about continuity along this line anymore. So, this function f is discontinuous on the y axis. So, let us look at any other function like this f of x y. It is much easy to prove the function is not continuous than actually proving continuity. And f x y is defined as 0 if x and y is equal to 0, it is just the origin. If so, when y is not equal to 0, it does not matter whether x is 0 or not, the function value, because suppose even x is 0, the function value is 0. So, when y is even 0, the function value is 0. So, when I fix my x and change my y, I get a continuous function, and when I fix my y and change my x, I get a continuous function. But the fact is that this function does not have continuity at the point 0 0. It does not have continuity at the point 0 0. Why do you think that this point does not have continuity at the point 0 0? Just look at take the line, approach 0 0 through this line, the line y is equal to x, and you put y equal to x here. When you put y equal to x here, so what would happen? So, f of x x would become 2 x square, and this will become 2 x square. F x x value is 1. So, difference between f x x and f 0 0 is 1. This cannot be made arbitrarily small. Given any epsilon, I cannot make it as small as I like, even though I can have points on y and x which are arbitrarily close to 0. You see, if I take a point here, I take a small ball around here, as small I can make the radius as smaller and smaller, but I will still find points from y and x in those intervals, points which are lying on the line y equal to x, but the function value cannot be made less than 1. So, this is a very crucial example which tells you that you see that when you are fixing x, it is not continuous, it is continuous. When fixing y, it is continuous over the whole domain, does not matter what is your x and y, and whatever x you choose once you fix y. But it is not true that this will be continuous at 0 0. So, that is the interesting fact, that So, as a function of y, if I fix x, for example, this becomes continuous, but at the point 0 0 when you are looking at the function as a function of two variables, it is not continuous because of this very simple fact. When I am putting y equal to x, it comes out to be this, and this is the distance, though points on y, well, the line y equal to x is arbitrarily close to 0 0, the difference between the function values cannot be made arbitrarily small, which violates the epsilon delta type definition of continuity. So, you see it is also important in this context to learn this epsilon delta type definition of continuity. Now, let us look into another example, for example, the last one for this class. We shall define, let us consider this for all x y with y strictly bigger than 0. You can say what would happen if y is negative, then it will become anyway positive, and e to the power x is defined when y is strictly less than 0. Okay, you can do for that. We are just considering this function, taking y strictly bigger than 0. Now, if I take a condition, now let me take a point. So, I am essentially looking at this, the function value for all these points except this line. I am not considering where y is greater than 0, I am only considering these points. This is what I am making my domain to be. I have defined this as my domain on which I have defined this function. Actually, there is this boundary, again on this domain you can define this function on the lower half plane, on the upper half plane you have this. And then what is important now is to observe, now take a point here, say xi 0. Basically, you are now looking at limit, suppose I look at the limit of f x y as x y goes to xi 0, what would this limit be? Because when this will go to 0, this whole thing is going towards minus infinity. So, it is e, this whole thing is going toward e to the power minus infinity, but when x goes towards minus infinity, so t goes towards minus infinity, e to the power minus t actually goes towards 0. So, this limit is actually 0. So, you can redefine the function. So, just like in the case, this is called this is the case of removable discontinuous point, this is a case of removable discontinuity. So, in this case, because I know this is the limit, I can say that f, I define f star x y is equal to f of x y for all x y with y greater than 0 and is equal to 0 for all x y with y is equal to 0. Of course, here also you have to take x not equal to 0, because here I am here on the line. So, but at the point 0 0, so of course, here x cannot be also 0, because if you have 0 0, so when I am taking the limit here, I am of course taking x to be a positive number, this xi is a positive number and I am approaching it from all these sides where x is a non-zero number, right. So, here my xi is positive, I could take it here also, say xi 1 0, then I can also approach with x negative from this side. So, x is either negative or positive, it cannot be 0, then only you have the limit this limit that I am circling now is true if x continues to remain non-zero, this or x continue to remain this. So, basically here you are doing, so this function now can be redefined, this for all points on the boundary you can remove the discontinuity and define it like this. So, only at the point 0 0 this function remains discontinuous, because this function is undefined at that point. So, you see even it is very interesting that on the whole line, which the function does not seem to have we have not defined it on the whole line, we can still redefine the function on the whole line, but still there will be this origin point where the function is not defined and is not continuous. But except that, except the point 0 0, we have now made this new function f star continuous all over. So, you see it is slightly tricky, and when you go through the examples and homework, you be very careful in handling these things. always you observe this, what happens. Now why do I say that f at f start 0 0 is undefined and this is also discontinuous? Why? Because suppose I now approach the origin through this parabola, I am approaching the origin through this parabola. For positive x, for x non-zero, for x non-zero, I am having y non-zero, right. And then if I go through this, so now what is f of x y in this case? When I put y as this, it is e to the power minus 1 by k. So this limit for various k's is just e to the power minus 1 by k. So that if I take the limit x and y, then this whole thing is now approaching 0 0. Of course, if this approaches 0, y is approaching 0, k I can take positive for the moment, does not matter, k is positive. So then for every different k, every different family, every different path that you take, so this is say for k1, this is for k2, every different path that you take, the limit is different, this will be the limit. So because the limit is different, there cannot be any limit obtained at f0 0, and the limit is not 0 0 either. In fact, the limit does not exist, you cannot have a limit, this limit itself does not exist, because for every different k, for every different path, you are having a different limit, and hence the function is not discontinuous, is not continuous at 0 0. Thank you very much, and we end our talk today.